get started here. I'm Yvonne, Staff for Science for the Public, and I welcome you to this program, Contemporary Science Issues and Innovations. And today we're recording from the Belmont Senior Center for the first time. And our topic concerns a remarkable image that appeared in the heavens fairly recently, and it was captured by the James Webb Space Telescope. It was a huge question mark. And so today, our guest who has provided all the explanation for multiple media places recently is going to explain what this is, what that image was, and the importance of that. This is Dr. Jacqueline McCleary, professor of physics at Northeastern University and a specialist in how gravitational lensing, which she'll explain, helps scientists probe the dark matter that is so mysterious in the universe. Dr. McCleary discusses here how galaxies and galaxy clusters might provide answers to the question of dark matter. We're very, very pleased to welcome Jacqueline McCleary.
Thank you for the warm introduction, Yvonne. So let's get into it. I know that we're all here because we're interested in the big questions, right? At least I certainly am. This image rightly got a lot of attention. As you can see, this is a very funny looking cosmic question mark, and it's a wonderful launching point for thinking about the mysteries of the universe. So by the end of our chat today, I hope that we will all understand exactly what's going on here and why this cosmic question mark and others like it are so important for our understanding of the universe as a whole. A little background, you will have to indulge me, I'm a professor and I have to professor away. So there are a couple of things that we need to understand. First, galaxy clusters. So galaxy clusters are massive agglomerations of galaxies like the Milky Way, some 10 times bigger, most 10 times or even 100 times smaller. Galaxies are social animals. They like to hang out in groups. Gravity pulls them together. And the total mass of a galaxy cluster can be 100 trillion to a quadrillion suns. These numbers are literally astronomical. They're huge. A megaparsec. It takes light about 10 million years to get from one end of a galaxy cluster to the other end of a galaxy cluster. That's mind-blowing to think about. Again, it's astronomical. These aren't things that we normally encounter in daily life. So galaxy clusters are really an extreme object to study. As we'll get into, their total mass is actually dominated by this mysterious substance called dark matter. And they also contain lots of hot gas, there's lots of stars, there's lots of galaxies. There's a lot going on. And something that makes galaxy clusters special is that unlike a lot of other things in the universe, galaxy clusters are still growing. Every day, every year, every million years, they get a little bit bigger. They collide and grow and merge. And this is an exciting time in the universe's history. So anyway, this is why I've made galaxy clusters my object of choice to study, my bread and butter. Something else that makes galaxy clusters special is that they act as cosmic lenses. Now, maybe it would be helpful if I explained what I mean by this. So massive objects like galaxies, even stars, and certainly galaxy clusters act as gravitational lenses. They bend space-time, and so light from a distant source, a quasar is a type of active galaxy, gets bent as it encounters this curved space-time. So, maybe it'd be helpful to back up. in the general relativistic picture of the universe, space is not something empty, but is something that moves, that can curve, and time is bound up into this four-dimensional substance we call space-time. Massive objects bend space-time in the same way that a heavy ball placed on a stretched out rubber sheet would cause a depression, would cause that sheet to curve. So when light encounters this curved space, it has no choice but to get curved as well. This phenomenon is called gravitational lensing, an analogy to the glasses that many of us are wearing today. Glasses change the path of light from the sun or a light bulb to our eyes. And very similarly, galaxies or galaxy clusters change the path of light so that they focus differently than they otherwise might. What makes gravitational lensing special more than just some physical curiosity is that the amount of bending that we observe of light from distant galaxies is proportional to the mass of the galaxy cluster. In other words, the heavier the galaxy cluster is, the more massive, the larger it is, the more extreme the bending of light behind the galaxy cluster will be. Now I'm sure you're all clever, we're maybe putting things together. It's difficult to weigh a galaxy cluster, right? You can't put it on a bathroom scale. Probably not even the scales that they use for elephants at the zoo. I can measure the shapes of galaxies, though. Looking at images like these, one of the first galaxy clusters observed by JWST, and I see these funny-looking, worm, distorted-looking things. These are actually galaxies that sit behind the galaxy cluster. So these don't actually look like this in real life. Their light is getting bent and distorted as they encounter the galaxy cluster. So by tallying up the number of arcs, the number of wiggly-looking galaxies, how stretched they are, I can deduce how massive the galaxy cluster is and eventually connect this to what the galaxy cluster is made of, what dark matter is. So gravitational lensing. There you go. That's a half a semester's worth of a lecture in 5 minutes. So if you'll indulge me, I'm a big JWST fangirl, as I'm sure many of us are. So it might be helpful to talk about why JWST is so special. So putting things in space is hard and expensive. Why do it? Well, what this schematic is showing us is the transmission of the atmosphere, the transmission of light through the atmosphere from short wavelength, very energetic light to long wavelength, less energetic light. Unsurprisingly, only visible light makes it through to the bottom of the atmosphere and to us. If we want to study distant objects, distant galaxies, which are brighter in redder wavelengths, we have to go up. We have to go above all of that pesky weather, that bright blue sky, and go into space. Hence JWST. So this is really, I think, one of mankind's great technological achievements. This mirror is 6.5 meters across, so 5 times larger than the Hubble Space Telescope mirror. And here's a little, here's a 6-foot-tall person, so a not-so-little person for comparison. And the design of this mission is incredible. It's the JWST, the James Webb Space Telescope, is designed to look at the infrared or redder than visible light portion of the electromagnetic spectrum of light. And of course, the sun is hot, There's no atmosphere to shield it from the sun's rays. So this funny-looking trapezoid on the bottom is a sun shield. This helps cool the telescope so that it doesn't get overwhelmed by this very, very bright, very hot source of infrared light called the sun. This is the mirror. This is a secondary mirror to help focus all the light from this gigantic mirror. And JWST lives in a very stable part of the Earth-Sun-Moon system called Lagrange Point 2, 1,000,000 miles from Earth. Lagrange points. They're essentially stable parts of the Earth-Sun-Moon system where the force of gravity is balanced out. And so something like a telescope can hang out without being too perturbed by one or the other thing. So this is a stable place in the solar system for JWST to live. So no servicing missions, however. So we had to get it absolutely right the first time. Some of you may remember the famous shuttle servicing mission to fix the Hubble Space Telescope.
How far away is it?
1,000,000 miles, over 1,000,000 miles. JWST, Lagrange Point 2. Yeah, it's 1,000,000 miles away. We're not sending anything out there. We had to get it right the first time. And remarkably, we did. So this thing had to be folded up. The sun shield had to be folded up so that it fit into a rocket, then unfold like origami in reverse. And somehow this worked. It took 10 years, a few $billion, but goodness was it worth it, at least to me. So to give you an idea of the power of the wavelengths of light that JWST looks at, this on the left is a crop of the famous pillars of creation as imaged by the Hubble Space Telescope. So this is not outside of the galaxy, but inside our galaxy. These are very dense columns of gas and dust, grains in between stars. And here in the middle, at the densest parts, are sites of star formation. In visible light, you can't see through it. JWST lets us see through a lot of this dust in the Milky Way and illuminates these hot areas, illuminates the sites where stars are forming. So left and right, JWST gives us access to a regime that we couldn't before. These are a bunch of gravitational lenses and other funny-looking galaxies observed by JWST. In general, the red color means a distant galaxy. So the redder the galaxy is, the more distant it is. And what we're seeing here is lots of red, stretchy galaxies, meaning that JWST is allowing us to observe very distant, gravitationally lensed galaxies that we wouldn't be able to see with the Hubble Space Telescope. And in fact, we'll see an example of this momentarily. So back to the question mark galaxy. What's going on here? We talked about galaxy clusters. This fuzz patch in the middle is actually the most massive galaxy of galaxy cluster max J, some long phone number. But I don't know who names these things. It's usually catalog and celestial coordinates. That's the phone number. This is the center of the galaxy cluster. And what this funny question mark looking thing is actually 5 repeated images of the same 2 interacting galaxies. So this is an interacting galaxy pair. You can see lots of pink and blue, which means that this galaxy is actively star forming. And this galaxy is red, which in this case means it's quite dusty. So now I'm in my natural professor mode. Let's go. So this object here is the most massive galaxy in the galaxy cluster doing the gravitational lensing of this remarkable source. These 2 are actually a pair of interacting galaxies. So they're in the process of merging into what will eventually be a large galaxy like this white one here. They're quite distant, and you see lots of pink and blue pretty dots. That means that this galaxy here, the round one that looks like a pinwheel, is actively star forming. And remarkably, 1, 2, 3, 4, 1, 2, 3, 4, 5. These are repeated images of the same sources. The distortion of space-time caused by this cluster is so extreme that it's causing multiple images of the same sources. And so this ribbon-looking red streak here is something that we on Earth are in a privileged position to observe because the alignment is just right. By the way, this thing on the bottom, the point of the question mark, just happens to be there. It's an interloper. It's not in the cluster. It's not being lensed, but it's just there for good company and helps us fill in the rest here. So all of this is very qualitative. If you'd like to see, just for the fun of it, a scientist's view, a researcher's view of this source, this is what it looks like. So because we are the way we are, we have to label everything. So A, B, C, D are 4 of the 5 repeated images of this remarkable source. So you can see the fact that they all have the same number in front means that they are the same source. And what this is showing are different instruments and different regions of the electromagnetic spectrum accessed with instruments on the James Webb Space Telescope. So the way that we understand that these are all the same object and not just some very funny worm-looking galaxy is by very carefully measuring the light of each of these and matching them to one another, matching the patterns, so we deduce this must be the same source. We measure its distance. We confirm that this source is behind the galaxy cluster. We know it's a gravitational lens. Then we put the pieces together. We do a little bit of math. We take advantage of Einstein's hard work. And based on the distance between us and the cluster and the distant source, and us and the distant source, we reconstruct the mass of the galaxy cluster. It's remarkably simple when I put it this way. And going back to Hubble Space Telescope for a second, again, just to illustrate the remarkable power of JWST, on the left is the Hubble Space Telescope view of this cluster. You could see it, but do you see any question marks? Any nice red galaxies? I sure don't. Looking at this with JWST, this is a zoomed-in area of this larger source here. This is a zoom-in of the question mark, shows that JWST, with its fine resolution and sensitivity to red light coming from distant objects, is what allows us to observe this remarkable system in all its glory. So this would not have been possible before JWST. So it was well worth the billions of dollars and decade of development it took, at least I think. So coming back, tying all these threads together, going back to the big questions that I and my colleagues try to answer with JWST and telescopes like it, these are more gravitational lenses, and yes, these are also repeated images of the same background galaxy, this arc, this arc. Gravitational lensing, like I said, allows us to weigh galaxy clusters. And I can also weigh a galaxy cluster by counting up the number of galaxies, looking at this in X-rays and finding out how much gas there is, making some assumptions about light and mass and galaxies, and tally up some, I'm almost done, and tallying up some number. You get some number of solar masses, a few million, maybe a trillion. Gravitational lensing tells us that the total mass of the galaxy cluster has to be 100 trillion. There's literally 10 times more mass doing the lensing than we can get by tallying up all of the starlight in all of the galaxies. So gravitational lensing is conclusive proof that there must be some extra matter. We call it dark matter. Actually, transparent matter would be a better descriptor because it just doesn't interact with light. If it were literally dark, we could see it, right? Because there would be something doing the absorption. So there's this stuff that doesn't interact with light, but does interact gravitationally, does bend space-time. And I'll end with this. This is where we are now. Gravitational lensing and also a whole host of other astrophysical observations tell us that there must be extra matter out there. There must be dark matter somewhere in the universe. And there must be about, depending on how you look at it, 5 to 10 times more of this dark matter than regular matter. What is it? We're still working on it. That's the big question we're trying to answer. So, yeah, we'll watch this space, literally and figuratively. And with that, I'll wrap up. I can sit myself back down and take any questions.
I think that's very nice. That was great. I think I'm going to skip the interview part because people have a lot of questions.
Sure.
I think we'll go straight to questions. If you just raise your hands, then we'll take them one at a time. Yeah.
What are some of the best guesses as to the nature of this dark matter? Is it another dimension or universe?
I love this question. So I'll repeat the question. The question is, do we have any guesses for what dark matter is? We absolutely do. And as physicists, we try to start with the simplest model possible and build in complexity. There were two competing ideas, machos and WIMPs. WIMPs, weakly interacting massive particles. So particles like, or analogous to protons, neutrons, and electrons, the things that make up atoms, but a different class that clearly doesn't obey or doesn't interact electromagnetically, doesn't do anything except interact gravitationally. The other option were machos, mouthful, massive compact halo objects, essentially black holes, dead stars, things that are massive and dark but star-sized, floating around at the outskirts of galaxies or in galaxy clusters. We're physicists, we preferred the WIMPs because, WIMPs, not macho. We started out with WIMPs, essentially a type of particle. We've been looking for WIMPs using particle detectors for about 20 years, and so far no dice. So we're slowly whittling away at what kind of a particle dark matter could be. And now, in the last 5-10 years, we're starting to expand our notion of what dark matter could be. For example, it could be a class of very ghostly class of particles called axions, which are almost like photons, have huge wavelengths, but detecting axions is hard. So those were our two guesses. So far, we've struck out. So it's back to the drawing board. That's an excellent question.
In the photography terms, how long of an aperture, how long was the aperture open to get a shot like that?
In other words, how long did the camera have to integrate? How much time was it open? Usually it's a few thousand seconds. So a few thousand seconds.
So it's open for a good while.
Yeah.
So what we're looking at is that there are a single source back there, but the lensing effect is changing in the system such that it appears to us as 5.
Correct. And these 5 lenses, these images are simultaneous. So you observe this system and you see the 5 lenses, and it doesn't vary with time. It's not something that you have to observe at just the right moment or the 5 images disappear. It's stable. So as long as you observe it for enough time, you will eventually find all 5 images.
And given that space is moving, that the objects in space are moving, looking at the same capture how many years down the road, would it look differently?
A billion?
We won't be around then, right?
Yeah.
Yeah, okay.
Well, yeah, in about 5 billion years, the sun will go red giant and engulf everything up to Jupiter.
Yeah.
But that's 5 billion years.
Yeah.
And I'm not being flip. Galaxies absolutely move, but the time scale for noticing a big difference would be tens of millions to hundreds of millions of years up to 1 billion years.
Could a catastrophic event within that space affect how it looked, like the explosion of a big star or something?
So, on the hundreds of millions to billions of year timescales, yes. Because if 2 galaxies merge, as we saw, did we look at merging galaxies? I guess we looked at these 2 merging galaxies. Galaxy mergers take place on timescales of millions of years to billions of years. So if the gravitational lens changes, the lensed images will also change. So a catastrophic event could be like 2 clusters merging or even galaxies merging at the center of the cluster would alter what this image looks like. It doesn't seem like that's going to happen anytime soon, but infinity is a long time, so it probably will happen at some point, just not in our lifetime.
Last one. Given that the aperture is open for 1,000 seconds, let's say if you revisit this capture and held it open much, much, much longer, would there be a chance of an appearance of another gravitational lens produced image?
So this is, again, a really interesting thing to think about. Probably not very large sources like these galaxies. However, the death throes of massive stars, supernovae, could appear over time because a supernova is something that occurs at a finite moment. So if you looked at this source in a year or 5 years or 10 years, it's certainly possible that a supernova, a dying star, either in the galaxy cluster or in one of these background galaxies, would appear. So that's definitely something that could happen. It's tough to predict ahead of time, but it is unmistakable when you see it.
The galaxy cluster is a lens, right?
Correct.
So you're deducing the mass of the cluster from the the image and the object distances to this lens?
Correct.
How far away is the cluster? That's the
Yeah.
image distance, right?
Yeah. So it is, I have it down in my notes. It is about 44 million light years away, if I
Oh.
recall correctly.
And
It's at
how
a,
do
it's
you
at a
know?
good distance.
How do you know the distance to the
Background galaxies?
to the images that you're looking at from the cluster?
This is another excellent question. So the first guess is the redder the galaxy is, the more distant it is. To make this a more precise answer, this is deep in the weeds, but essentially we look at the patterns of absorption and emission lines in a spectrum. Are you familiar with the notion of spectroscopy and spectra? Okay. We look at the spectra of the galaxies and look for patterns of emission or absorption lines, so for everyone else, spikes up or down in brightness at a given wavelength associated with a given element and something happening inside an atom of a given element. We look for patterns in these because these emission or absorption lines, these spikes up or down, usually happen in pairs or in triplets. We look for patterns in these. There's a few that we are generally fingerprints, and we look for the distance between where we actually observe them in the spectrum and where we would see them if we were looking at these atoms here on Earth. And based on that distance, in wavelength, we can arrive at a distance in space. So redshift, if you're familiar with the idea.
It seems to me you have to know them fairly accurately, though.
That is absolutely correct.
And can you get pretty good accuracy with these measurements?
Yes, because JWST was built for this. There's multiple instruments on board, not just a camera, but dedicated spectrographs designed to take very high resolution spectra of astrophysical sources.
So once you have the I and the O, the image and object distances, how do you actually calculate the mass of the cluster?
Now I wish I had added a slide with equations.
Is that Einstein's field equation? Is that what you use?
So I would love to say that, yeah, I get out a pencil and paper and calculate the solution. But for the case of strong lensing, we use a somewhat simplified form. Essentially, distance between, if I can go back to something, sorry,
No.
bad professor. Here we go. So, oh good, I did keep this on there. So this Greek letter theta, I know that you know I'm trying to make sure that I'm carrying everyone else along too. This Greek letter theta represents the extent, so how stretchy this galaxy is. This letter B is distance from the center of the cluster to the stretched out galaxy. And note that there's always a counter image. If I have an arc on one side, I need to look for the arc on the other side. So there is a proportionality between the the lens source distance and us source distance, the impact parameter, as it's called, the distance between the center of the lens and the arc, and the stretchiness of the arc. And so there's a fairly easy equation, it becomes algebraic, where m is equal to some fundamental constants times theta divided by the distance to the arc.
So you've now determined the mass of the cluster.
Correct.
How do you differentiate or distinguish between what part is the visible mass and what is the dark matter?
Again, excellent question. So this requires multiple observations. Galaxy clusters are actually dominated by hot gas. So we have to, which shine in X-rays. That's right, X-rays, the thing you get at the doctor, is just a different wavelength of light. It's not like a totally separate particle. So are radio waves, by the way. It's all light. Look at this cluster in X-rays. How bright is it in X-rays? There's a relationship between how bright this is in X-rays and how much gas there is. Tally up the starlight, count the number of galaxies, and have some well-motivated assumptions about the relationship between brightness in optical, in visible light, and the mass of stars. We know stars pretty well, so these assumptions are actually pretty good. So weigh the gas, weigh the galaxies, the difference is dark matter. This is an excellent question. Yeah.
Okay.
Sorry.
There's dark matter out there. The question is, what is it? My question is there any dark matter in the neighborhood?
Ooh, yes, absolutely. So
Round.
this image here is supposed to get us thinking a little bit. It came out a little pixelated on the screen. This is an artist's conception. This is Andromeda, the nearest, brightest galaxy. And what these dark splotches are supposed to represent is the halo of dark matter in which the Andromeda galaxy and all galaxies like it are sitting. So galaxies, including our own, are embedded in halos or clouds of dark matter. It's not just something that sits in the center, that envelops a galaxy cluster. It envelops individual galaxies as well. So there is dark matter continually passing through the disk of the Milky Way and galaxies like it. And in fact, my particle physics colleagues' attempts to detect dark matter particles rely on the fact that there must be dark matter passing through the Earth at any given moment.
So I have a question that's more philosophical. You spend your days and maybe some nights thinking about these massive things in space that are all around us. How has that affected the way you think about humans and the Earth? And as you teach your students, how do you see their thinking changed by thinking about these scientific explorations?
That's a beautiful thought. So it's hard not to look out and see the vastness of space and then think about how silly our internal divisions, squabbles, problems must be. You know, we're all we have on this planet, right? And so looking at these objects in space makes us think, at least makes me think, you know, we're all brothers and sisters. I want us to be united. And at the same time, it's also nice to think about something good that mankind does collectively. It took a lot of concerted effort from a lot of people. You, the public, politicians, administrators, scientists, engineers, to build telescopes, to build observatories like the James Webb Space Telescope. We decided that science was worth that much work. And I think that that's something beautiful. You know, in the Middle Ages, we built cathedrals. In the modern day, we build observatories in space. And we decide that it is worth the money, it is worth the time. You know, I think that that's beautiful.
That's right. Good.
And my students, as you can tell, I live and breathe astronomy. I love this. And I think that in teaching these classes, as I teach these classes, at least my course reviews suggests that the students get engaged too, because I'm engaged and I like it. And they learn something about the universe that they didn't when they came in on day one.
I know this has only been up there a few years, and I had read the other day that it might only last 10 years. What things could go wrong with it? Obviously, we can't go up there and fix it. So when this stops working, what do we do next?
The principal concern is the loss of coolant. So everything glows in infrared. And so the telescope, the cameras have to be actively cooled in order to be able to measure the same wavelengths of light that the telescope emits, because it's not at absolute zero. That's the principal operational limit. What that means is that we will lose sensitivity to a certain range of wavelengths. Not all of them, however. So we will be restricted to, you know, less infrared, but we'll still be able to use it. Something else that could happen is, you know, if you want to go to the catastrophic, a wandering asteroid, you know, wandering meteorite impacts that could damage the mirror as well. That would be sad, but fortunately that's less of a concern at L2 than it might be elsewhere in the solar system. But yeah, the principal concern is loss of coolant.
This is very interesting. Lately I've been reading quite a bit about the possible coming soon supernova of Betelgeuse.
Can't wait.
Yes, and I wanted to know, is there much that the scientists expect to learn from that event relating to the things you were talking about today, or is it something different?
Well, supernovae are actually, especially something as nearby as Betelgeuse, will actually be bright in initially X-rays and even gamma rays, which are the very highest wavelengths of light, and eventually visible. So this is something where Hubble, if it's still floating, would actually be useful, as well as space-based high-energy astrophysics observatories. I think what we would gain is an instantaneous view a near instantaneous view of the way that these supernovae, the way that Betelgeuse, the way that the explosion of Betelgeuse, which is a massive, almost dead star in Orion. It's Orion's right shoulder. It glows bright red if you go outside and you look at it. And it's going to go supernova. It's going to explode soon in a dramatic event that you'll be able to see during the daytime. Please, 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 I want to see it. So we'll learn a lot about supernovae. It's probably less relevant for what I do, but stars are as cool as galaxy clusters. There's a lot of physics going on in there, so I really hope we see it.
I hope so too. People, we need to.
With the telescope or naked eye?
Both. So visible, it will be visible with the naked eye.
Very visible, I think, yes.
I'm sorry? It'll look like a big star? Yeah. And it'll be like spatially extended. It won't just be like, it'll be like sun-sized. And it'll last for a few weeks.
Yeah, it's going to be great. And then they'll have great photos of it from space, too.
I'm sorry? I wish. Okay.
People, I'm sorry, we need to close down to let her get back to school there and so on. But I appreciate very much your questions, and thank you very much for your wonderful attention.
Thanks for having me.